Okay, so welcome to EE 42 and 100. How many of you have signed up for EE 42? And 100? Okay, it's roughly an even mix. So we have 230 odd students in the class. That's a lot. Okay? We will try our best between us, and I'm going to tell you what the ground rules are in a bit, to make this class interesting. For how many of you is this the first EE class that you're taking? Okay. How many of you have taken some other EE class before? I should have asked that question, I guess. Okay. All right. So we will try to make this interesting. My goal in this exercise is to do two things. One is to teach you the course material, and two is to make you think that EE is actually reasonably cool. Okay? And hopefully that'll convince some of you, probably not all of you, to take some more EE courses. Okay? So that's what we're going to do. Now, let's start. Who am I? I'm Vivek Subramanian. I'm a professor in electrical engineering. My office is in the new building, which is Satarja Dai Hall. It's been open for about a year now. And it's 513. That's on the 5th floor. It's kind of difficult to find my office, which is nice. You get out of the elevator, you go to the right, and then you head down the hall. Okay? And there's a few faculty offices in a corner there that nobody knows about. One of those is mine. Okay? And I'm generally around a fair amount this semester, though I do tend to travel quite a bit. But I will try to be available whenever you need to see me. You're here, so you know when lectures are. By the way, I apologize in advance. I know taking classes on a Friday afternoon is not ideal. I did not schedule this. I would have scheduled 8 o'clock in the morning on Tuesdays and Thursdays. Okay? That is my favorite lecture time. But anyway, we'll live with this. This is fine. All right. My office hours will be Thursdays 2 to 3 and Fridays 3 to 4. Okay? If you're not able to make those office hours, you can always email me for an appointment. So the way to do that is the following. Go to that web page, and it has my schedule on there. So don't email me before you look at that. Don't say, can I meet with you? My answer will be yes, but when? Okay? What I want you to do is go to this web page, look at my schedule, find a couple of slots that appear to be free, and then email me and say, are you available in those times? Can I set up a meeting? And assuming those slots are actually free, I will respond and say yes, and then I will wait in my office to meet with you. Okay? Periodically, you will find, not for office hours, so office hours I'll actually stay in my office, but periodically if you come to meet with me, there may be notes on my door saying I'm down in the coffee shop. Okay? And if that's lucky for you, because then I'll buy you a free coffee if you come downstairs. Okay? All right. So that's the general outline. We have several TAs for this course, but we don't have enough. So I am right now in the process of fighting with the department to get more TAs. We will get them, but we have a few of them here. There's going to be some consequences based on the number of TAs we have. So with the TAs mind standing up, and I will just point them out briefly. So 1, 2, Minhee's in the back. Okay. So we have Kyle in front, Jake over there, Michael there, Minhee in the back. We have an additional 3 TAs assigned right now who are not here, and I'm trying to get 2 more. Now, what does that mean? We do not have enough TAs for all the labs that were put on the schedule. We will not, even if they gave us the 2 more TAs I'm asking for. So we are going to have to do 2 things. First, for those of you who are signed up for the Monday or Friday 8 a.m. labs, we're going to cancel those labs. And I'm going to roll them into the Wednesday lab. I'm going to ask the department to just dump them in automatically. So you don't have to do anything. You'll get dumped into the Wednesday lab. If Wednesday doesn't work for you, and that's the Wednesday 8 a.m. lab. If that doesn't work for you, then you should just manually go and change your lab, pick another lab. The second, the Thursday 8 a.m. lab will be canceled. Okay? So you're going to have to go find another lab. I apologize. Unfortunately, there's just constrained resources. We don't have enough TAs to run all the labs. Okay? If that's a problem and you have some creative way of solving that problem, come talk to me. I'm happy to learn about it. Okay? But as of right now, our plan is Monday, Thursday, Friday, 8 a.m. labs are gone. Okay? All right. So the TAs generally won't attend class, but they will have their discussion, and they will have the labs. Okay? And they will answer email, and they will monitor the B-Space discussion lists, and so on and so forth. Okay. How many of you are how many of you are signed up for 42 but are not taking 43? Okay, that's too bad. So this is our project, okay? So we've changed the labs a lot this year. So here's what you're going to do. You're going to start out the labs. They're brand new labs. Most of them are completely new. Some are partially new. And we've got a whole new framework. The idea was to make labs that you would find fun. So you're going to start out by learning some basic skills, like learning how to use a soldering iron without burning yourselves, things like that. And then you are going to start working on modules which will ultimately build to a project. And the project is actually really cool. You are going to build an EEG. You know what an EEG is? An EEG is used, you put probes in your temples, and you use it to read brain waves. And we are going to try to set up an EEG whereby using your optical nerves, so essentially by moving your eyes around, you can move the cursor on a screen. Okay? So, and the final test on the project is going to be the professor for EE40, Michelle Maharbiz, and I will be your test subjects. We will put the EEGs that you make on us, okay? And we will see if we can make cursors move. And if you kill us, there's no final exam, right? So it's pretty easy. All right, so that's the plan. Now, we had talked about a few other options. I'm going to ask you some questions, not for this year, but for next year. So one of the projects I had proposed, which got shot down for good reason, was to make cell phone chargers. So you know that your cell phone right now, you plug in the little charger. It turns out it's relatively trivial to make a little plate that attaches to the back of your cell phone, so you just put it on a table and it charges off a pad. Okay? We were going to do that, but we were advised not to do it because we were worried that you guys would sue us if you blew up your cell phones. Okay? Does that sound like an interesting project? Would that be something cool? More useful, right? So, okay, there'll be a few others that I have that every now and then I'm going to talk about. As you work through it, I'll get feedback from you, and next year we'll change the projects. Okay? Each year we're going to change the projects. Yes, question? I think there's space. Okay? So, yeah, you're just looking forward to shocking me at the end of the lab, but at the end of the final. But no, I believe there's lab space still available. Okay? All right. Okay. So, what's the textbook? We changed the textbook this year. The textbook we're using is by Ulabi and Maharbiz. Professor Maharbiz is in our department. He moved here from Michigan. So, we've changed the text for several reasons. Frankly, the two main reasons I changed the text was I like the examples that are in the text. It has a bunch of real-world examples that I think are kind of interesting. I'm not going to ask you questions about those on the tests, but it's interesting for you to read. Also, I know you are spending a lot of money on textbooks, and this is the cheapest EE40 level text I could find. Okay? So it's relatively cheap. The company that publishes it is actually not making much money on it because what they want to do is get you to buy the text, and then they also make software and hardware kits, and then they want to try to get you to buy those. Okay? But you're not going to do that, so you get the textbook relatively cheap. Okay. Now, the other advantage for me and also for you is we've therefore been able to align EE40 and EE42. Okay? So the lectures will run essentially in parallel. This lecture, is the webcasting guys here? Is anybody here who's handling webcasting? They are theoretically webcasting this course, okay? I have no idea what that means. But what that means is if you miss the course, you should be able to make it up. Also, if you miss it, you can probably sneak into the EE40 lecture and essentially be on the same page, okay? And every now and then we may trade off just for variety and for scheduling reasons. It's possible that sometimes I may teach 40 for Michelle, or Michelle may teach 42 for me. That may happen periodically. Probably not too much, but it might happen. And really, from an aesthetic perspective, there's no reason for us to have separate classes for 40 and 42 and 100. I mean, The reason you're not in 40 is because you're not indicating electronics as your primary interest, but it doesn't mean you're not just as capable of doing it as students taking 40, because you're all intro students. So it's sort of silly that we have 3 separate courses. Now 42 and 100 are essentially tied to each other. They have separate curves for grading, and that's fine. But really, we'd like to get all 3 aligned and just have separate curves for each of the courses. Yes, question? Same text, same notes, same syllabus, same project, same labs. 100, 40, 42. All the same. Okay? And we're hoping that we can get things merged even better than that. All right. So if you have the text, that's great. If you don't, I do recommend getting it. You're going to find as I go through the notes, my notes are intentionally sparse. What I mean is I don't give you all the information in the notes. 2 reasons. 1, I want you to actually take some notes yourselves, so you'll pay attention. And 2, I think the text is actually really well written, and you'll benefit from reading it. Some of the examples are really interesting. Okay. As far as the course is concerned, we will follow the context, the text pretty much start to finish. Okay? So if you want a syllabus, that's the syllabus. We're going to pretty much follow the text. As I said, I will be giving you notes. The notes are your primary guide. Just to give you some perspective. When I make your exam questions, I'm not even going to look at the textbook. Okay? I will make your exam questions from my notes. So your notes are your primary guide, but they are intentionally sparse, which means I will say things in class that are not on the notes. And that's still fair game for the final or for the tests. Okay? So it's your responsibility to be in class or watch the webcasts. Okay. Now, this is a reasonable time. It's 4 o'clock. You know, it's not like an 8 o'clock in the morning class. You know, and you'll find that I'm pretty good at keeping you guys awake because I'll start throwing stuff at you if you go to sleep. Okay? So you know, we'll keep each other interested. All right. Now, EE 100 is, of course, is one part of this course, and this is how it breaks down. 15% homework, 40% tests. The tests will be about once a month. I believe in a lot of tests for the following reason. 2 reasons. 1, it allows me to see how you're doing. And so I can adjust to, if I find none of you get it, I can try to figure out what I'm doing wrong to fix that. Okay, and try to recover relatively quickly. If I wait 2 months for your first test, I may have lost half of you by then. And 2, frankly, it allows you to screw up, right, and get away with it. If you screw up one test, it's only one test out of 4 or one test out of 5. So it doesn't hurt you as badly. I'm not going to drop any test scores, but at least it minimizes the impact. You know, Friday test, Thursday night you were out drinking, you're okay. All right? Okay, final exam, 30%, and labs are 15%. E42 is very similar. Of course, there's no labs. That's E43. Okay? So for those of you who are taking 42 and 43, the labs are separate. 42 doesn't have its own labs, obviously. The tests are the same. Okay? All right. Just some general policies. I do not give makeup exams. If you need to, that doesn't mean I'm going to ding you if you miss a test. Okay? Here's the deal. If you clear your absence ahead of time, you have something urgent that you need to take care of, and you can give me a documented reason for it, I'm fine. I will basically just average your test based on your other tests. And I use a pretty sophisticated averaging technique. My tests tend to vary. My first test is always really hard. Okay? There's a reason for that. I want to drive as many of you away as I can. So I make the test, well, I'm kidding, but I do make the test somewhat hard, the first test, okay, just to get a feel for how you're doing. The second test may be somewhat easier. If you miss the second test, then I don't want you to get dinged because the first test was hard and the average got applied to your second test. So I actually have a weighted average system I use. I found it works really well. If you end up missing a test, we can handle it. If you miss a test without a prior excuse, if you are sick, then you just get me medical documentation to attest to that, and we'll do the same thing. No problem. Okay? But I do not give makeups. Okay. Homeworks. There will be a homework roughly every week, not exactly. Okay? It'll probably end up being twice every 3 weeks. And you can miss one homework. Or you can do all your homeworks and then I'll drop your lowest score. Okay? For cheating, you know the policies in the department, or I assume you know the policies in the department and on the campus. If you cheat, I go for the maximum penalty. You can ask students who have, well, you can't ask them, they probably won't admit to it, but you can ask students who have caught cheating in the past, and I will nail you to the wall, okay? I will go after you with everything I have, if the goal is to get the maximum punishment allowed by the university. And if that means expelling you from the university, I will go for that. If that means giving you an F in the class, I will go for that. Yeah. Okay? So, read the academic dishonesty policy. This is the last time I'm going to mention it, okay? For better or worse, I did my graduate work at Stanford. Stanford actually has an honor roll, an honor code where we would say, it was the weirdest thing. I went to a big state school for undergrad, and then I got to Stanford, and the first test I took, the professor walks in and says, all right, take your test. It's a nice day outside. Go do your tests outside and come back. That was wonderful. But you got to wonder, doesn't that encourage people to cheat? And it didn't. I would love to have that kind of policy here. But apparently we don't trust you, okay? So I'm not allowed to do that. But de facto, I trust you not to cheat, okay? I'm not going to mention this again. I'm going to trust you. I'm going to do my best to be a good teacher to you and make this material interesting to you. And I trust you to be good students and follow what you know to be the right policies, okay? All right. So what are we going to do today? Today is going to be a mixed bag, today and the next class. I'm going to spend a little bit of time motivating the course, and I'm going to introduce some terms. Most of them you've probably heard of, but we're going to introduce them in a formal way, okay? So most of you have cell phones. I would assume all of you have cell phones. And of course, the cell phone has become an extremely important device in electrical engineering. Anybody know what the biggest company in the world is today? Yeah. No, it's not anymore. It was briefly. Today, it's not the biggest. The stock price went down as it got dropped, right? Because Jobs left. So it went up, but it's still not up to the peak level. Yeah. I think it's actually Exxon's the largest. Okay. But Apple was briefly the largest company in the world. Okay. You can see how important phones are. They've become really important. To give you some perspective, the computing power of an iPhone or an equivalent smartphone exceeded that of a mainframe from 20 years ago. Okay? These things are amazingly powerful. And then you're holding it to your ear and you're frying your brain. So, okay, but these things have become extremely important. So you're going to find through the course that I will use a cell phone as an example to talk about some of the concepts that we talk about. Okay, now, you're getting into the right groove with me. You'll see that I ask a lot of questions, and I want you to answer. If I find that you're being pretty responsive now, that's great. If I find the class is not being responsive, I will start calling on people. If I find that it's always the same people answering, I will start calling on people. If I find that nobody's answering, I'm just going to stare at you till you answer. And have no doubt, I will stare at you for 15 minutes, okay, till you answer. It doesn't bother me one bit, okay? So, all right. You're welcome to try, okay? All right, so let's talk a little bit about some of the things we're going to learn about in this course. You are not going to learn about all of this in this course, but I'm going to talk about some of the things you're going to learn about in this course, and then I'll relate it to some of the other courses that you're going to see. If you look at the internals of a cell phone today, broadly speaking, it has several things. It has the circuitry associated with communication. Okay, that's all of this. This is the circuitry. It's essentially a bidirectional radio that's used for transmitting and for receiving. It has a huge digital component. It has a digital component that is responsible for all the software that you run. And it actually has a fairly large microprocessor on the inside. Anybody know on the Apple iPhone who makes the microprocessor? No. Samsung. Who said that? Yes, correct. Samsung makes it, which is really interesting because now Apple and Samsung are suing each other. Sometimes I don't understand this, but anyway, Samsung does make it. Foxconn makes the iPhone when they're not committing suicide. But so sorry. Do you know what I'm talking about? Yeah. Okay. Yeah. Yeah. They seem to do it relatively routinely. So anyway, but yeah, no. So Foxconn does the assembly. Samsung makes the chip. Okay. It's actually a remarkable chip. It's got multiple processors inside it. I believe it has 4 ARM processors inside it. So it's basically got 4 individual CPUs inside which are doing different things. Okay? And a superset of that is used in the iPad. It's actually a very similar processor. Okay. So there's the digital part. Then, of course, there's lots of memory because we use a lot of memory in what we do. Then there's the human interface, the touch screen. We'll talk about that. And then there's, of course, the power system, the battery, the charger, etc. And then there's all the I/O stuff other than touch. There's audio processing. There's the video processing capability. All of those things built in. So we're not going to learn about all of those, but we'll learn about some of them. Okay, let's take one example now to start, and then I'll introduce some of the concepts you're going to learn about in the next week. All right, let's pick the touch screen. Okay. Most of you will probably say that what was revolution... Actually, most of you are not, probably not. For how many of you was the iPhone your first phone? Oh, okay. I thought it would be the majority. I'm surprised. Okay. All right. The iPhone... So what many people... Actually, how many of you have a Windows mobile phone? Is that Windows Phone 7 or Windows Mobile? Really? You're running Windows Mobile 6? Wow. I have one of those. It's sitting in my garage. But no. It's actually Windows. What's the big difference between the interface that Windows used for the Windows Phone? And I love that Windows Phone. Okay, I used it for years, and it took me forever to move to Android just because I had everything set up to work on it. What's the difference between that and a more modern OS such as Android or iPhone in terms of the touch interface? It's not multi-touch, and it responds to fingers as opposed to a stylus, right? Now, it turns out the Windows Phone could use your finger, depending on the model, but it was really designed to work with a stylus. Okay, now, it's not multi-touch. Anybody know how does an iPhone screen or a general cell phone screen sense your finger? Yeah. Heat. No, unfortunately, heat doesn't work. Yeah, at the back. Capacitive. Okay. What does that mean? Yeah, sure. Almost. Okay, so he said it reacts to the electrical charge in your finger. Did I say that correctly? Was that what you said? Okay. That's not actually quite right. That would be an electrostatic interaction where it's responding to the charge. Rather, it responds to the charge that your finger pulls out of the panel when you put your finger on it. So basically, the way the iPhone touchscreens work, there's a series of rows and columns, and on the rows and columns, there's a capacitance between each row and column intersection. When you put your finger on top, you bleed some of the charge out. So it's actually not the charge on your finger, it's rather the ability of your finger to pull the charge out. Okay? And what Apple really did was they figured out a way to use that to develop multi-touch in a way that actually could be combined with a remarkable user interface, this pinch to zoom and things like that, and make an interface that people like to use. So that's essentially what they did. Now, they're using capacitance. So you already defined something for me. I asked him, well, what's capacitance? And he said it's something related to charge. So we've now got 2 terms that we're going to discuss very soon, capacitance and charge. So early in the course, we are going to talk about very simple circuits. We're not going to talk about capacitance for a little while. We're going to talk about simple circuits, resistor-based circuits. Then we'll add capacitor-based circuits, and so on and so forth. Okay? And so really, by the time we're done with this course, you'll be able to explain perfectly how a multi-touch system, or at least how the underlying behavior of a multi-touch system is detected. Okay, so that's that human interface. We're not going to spend a whole lot of time, in fact, we're going to spend almost no time talking about details of RF communication. But essentially what we do in a modern cell phone is, let's say you have a signal coming in, we amplify it, we sort of clean it up, we get rid of all the noise and avoiding nearby signals, and then we extract the information on it. So if it's a voice call, we extract the voice information. If it's a data transmission, we extract the data, we convert it into digital domain, and then everything is handled by that microprocessor. Similarly, in the outbound direction, when you speak into a cell phone, it's all digital. which means your voice goes through a microphone. It's converted to a voltage, which is then converted to a digital signal. I'll ask a question about that in a second. That digital signal is then processed to clean up your voice, to encode it as needed, and then it's sent out, put onto the carrier that it needs to be on, and then it's sent out to the cell tower that receives it. Now, I'm using these terms digital. When I say digital, and I said analog briefly as well, what's the difference? What does that mean? What's digital? What's analog? Yeah.
So digital, like, there are like the gaps between the data, like 1 and 0. There's no 0.5.
Okay.
But in analog, there are like the data is like all connected.
Okay. That's a perfectly good way to describe it. A digital system would be a system, at least digital as we use it for most applications that we're going to talk about. A digital system is a system with discrete levels. And for example, if I have a 5-volt power supply, a digital system might represent 2 levels, one level at 0 volts and another level at 5 volts. An analog system will be continuously variable. For example, a sine wave would be an analog representation. Most of you have probably heard, sometimes when you go into a system with a poor audio capability, you go into a room, like you go into a club and they're playing music, and the music goes off and you hear this hum. This sort of buzzing sound, and it just is always there. Anybody know what that is? Yeah. Correct. And that is a sine wave. Okay? So the AC in the power lines is a sine wave. It's 60 hertz, so it cycles at 60 times a second, and the human ear can hear that. Actually, as you get older, this is the beauty of getting old. Pretty soon I won't be able to hear it anymore. Okay? So as you get older, your ability to hear low frequencies drops off, but you guys can probably all hear 60 hertz without a problem. Most people can hear 60 till they die, but you start losing 20, 30, 40 as you start getting older. Young babies can often hear below, certainly well above what you can hear. Baby's hearing is usually much better than even you. Okay, so that's digital to analog, and we're going to spend most of the course talking about analog systems, but we will spend a little bit of time talking about digital. I also mentioned we will use amplifiers. An amplifier is you know what an amplifier is qualitatively. It's a component that is used to expand a signal. So if I come in with a signal that, let's say it's a 1-volt signal, it's a sine wave that's going from 0 to 1 and down to -1 and 1 to -1 and 1 to -1, an amplifier might expand it to go from +5 to -5, for example. And so we will spend time talking about amplifiers, and in fact, in your first lab that you're going to do next week, you will build something using some of these. And in the labs, you're going to do a lot with the amplifiers. By the way, I should mention before I forget, no discussions next week. Okay, I've had several emails. There will be labs next week. There will be no discussions next week. Okay? Okay. So, how does this relate to EE? Why do we tell you about these cell phones? Because there's a lot of courses in this department that we teach that cover the various things that you would care about. In this class, you're sort of learning the underlying basics that will help you understand everything else. But where do you go from here? If you want to learn about designing analog circuits, such as the amplifiers, etc., the radios, etc., you would take 105 or 140, and then to learn about radios, you would take 142. 105 and 140 focus primarily on analog circuits. There's a little bit of digital in 105 as well. 142 is purely about RF. If you want to learn about the transmission of radio waves, and you want to learn about how those radio waves travel from the antenna to the tower, you take EECS 117, which is the electromagnetics course. Then if you want to learn about communication protocols, how communication actually happens once the signal gets to the tower, how multiple phones are able to live and coexist with each other, you take EE 122. If you want to learn about digital systems, namely how the microprocessors are architected, etc., you would take CS 150. And then the subsequent courses from there. If you want to learn about how to design digital circuits, for example, you would take 141. So there's a whole range of different courses that we have. Hopefully some of you will be interested enough to follow up with some of these. These are a good range of courses, and they teach you different things that are relevant to understanding how devices that you use work. Okay. So what are you going to learn in the process of learning about EE? What do EEs discuss? Well, we tend to break the world into layers, and I'll explain what that means when I talk about professors in the department, for example. We tend to break the world into three major layers: devices, circuits, and systems. This class is primarily a circuits class. Okay? The devices class would be, for example, EE 130. In the devices class, you learn about how individual devices work, such as transistors. You'd learn about how they actually work. You'd learn about how electrons and holes move around, or photons, and you'd learn about how individual components work. Circuits combines these things together. So we take multiple transistors, we make a circuit, we make an amplifier. So that would be a circuit. And then the next level up is systems. And at the systems level, you start looking at big systems where you have, for example, architectural issues. You're implementing microprocessors or systems related to communication protocols, and so on and so forth. If you look at the way the department is divided, how many of you are EECS students? I would think not too many. Yeah, okay. How many of you are CS students? Okay. All right. So if you look at within the department, if you look at the CS side, of course, they have their own. All these layers are the EE layers. If you look on the EE side, roughly half our faculty fall in devices. In fact, more than half. 2/3 of our faculty fall in devices and circuits, and about 1/3 fall in systems. Berkeley has traditionally been really strong in devices and circuits. And if you take our 50-odd faculty members in the EE side, the vast majority of them fall in these areas. As we move a little further along, most of you are, I assume, in your second year. Actually, how many of you are first-year students? Not too many. Okay. Most of you are probably in your second year. You're not yet thinking about it, but at some point, some of you will think about graduate school, and you'll want to do undergrad research to make that happen. So when you get to that point, this is a way to think about what you're interested in. If you're thinking about undergrad research in the EE side, well, you figure out for yourself. Do you like the devices work? Do you like the circuits work? Do you like the systems work? And then you go talk to professors in that area. Okay, so let's talk a little bit about some interesting side notes. Just as a deviation from the text, I'm not going to ask you questions about this part on the test. This is just to give you a little bit of history. EE is characterized by one thing. People, over the last 100 years, people have made a lot of money as EEs. Okay? Even today, as a bachelor, BS graduate, the average starting salary for an EE tends to be higher than most other engineering majors. That's true. Right now, it's actually pretty good, though. It's surprising. What happened was they laid off so much that everybody's hiring like crazy right now. But anyway, so it's not a bad field to be in. I don't know how long that'll stay true, but it's certainly true today. What that means is, when there's a lot of money to be made, there's a lot of weird people. And so I'm going to tell you a little bit about some of the weirdness that happened, because it's just interesting. Like when you read about music. Okay, so Van Gogh is a very famous painter. What do you know about him? Yeah, everybody knows he cut off his ear, right? I mean, if he had not cut off his ear, would he be that famous? I don't know, right? So there's a lot of interesting characters in EE as well. So we'll talk about them just briefly to give you some perspective. I'm going to start by suggesting some experiments that you can do at home. How many of you live in apartments? Okay. How many of you don't like your landlord? All right. I have some good experiments for you to do right before you leave. Okay? Okay. So, I'm going to introduce some things that you can do at home to learn what it's like to experiment on electrical engineering systems. We'll start by talking about piezoelectricity. Piezoelectricity is defined as electricity generated by mechanical deformation. What that means is if I bend something, for example, while I'm bending it, it momentarily generates a voltage across it. A lot of systems show this, it turns out. Piezoelectricity is very well known. Piezoelectricity turns out to be actually an analog of piezoelectricity called piezoresistivity. Turns out to be very important for something that many of you probably use. Anybody know? There's a particular type of printing. Most of you probably own a printer like this, where we really need piezoelectricity. This phenomenon is very important. Yeah. Yeah, inkjet. Not all inkjets, not HP inkjets, but inkjets by Epson, for example. Each time the drop is ejected from the inkjet printer, it's actually a piezo element. It's the reverse of this. Here, you generate electricity by deforming. In the inkjet systems, you apply electricity and then it deforms. And that pushes out a drop. Okay? So this is something that many of you probably own. I said HP does something different. Anybody know what HP does? How's the HP printer different from the Epson printer? Yeah, it's on sale. Okay. Anybody know? Okay, so the HP printers actually use what's called thermal print. It's a bubble jet, which means what they actually do is they heat up the ink inside the canister, and it boils right around the heating point, and it generates a bubble, and that pushes the drop out. Okay, so instead of using this mechanical deformation, they actually heat it to cause it to come out. There are two competing technologies. They have advantages and disadvantages, but it is what it is. Okay, so you can make your own piezo systems. There's a material you can buy commercially. It's very easy to buy. You can order it online, called Rochelle salt. It's potassium sodium tartrate, which is that equation right there. And it turns out, if you take a crystal off it and you hit it with a hammer, you can actually generate kilovolts. Okay, so it's extremely high voltage. So how do you do that? Take washing soda, you take cream of tartar, okay? And you take water, clean water, all right? And you heat them together until they stop bubbling, and you filter it to collect the residue, and what you've got is Rochelle salt. It's this gunky powder. That on its own is not useful for generating piezoelectricity. If you hit it with a hammer, nothing will happen except it'll sort of fly up in your face, okay? All of these things you can buy, right? I mean, you can buy these at the grocery store. But here's what you do. You make a crystal. So you dissolve it in water, and then you go through that powder stuff that you had, and you find one piece that looks reasonable. And by that I mean it looks like it's a little tiny crystal, okay? And you tie it on a string, and you suspend it in the solution of the remaining powder, and you just let it sit. And then you'll get a nice crystal. It'll be about this big. This is not a crystal I grew. This is a picture I just found, okay? I've tried to do this. I've never been able to get crystals this nice, but you can make decent crystals. And then you hit it with a hammer. And you hit it with a hammer. I'm going to ask you a question in a second to see if you can get the cultural reference. I'm sure none of you can, but you hit it with a hammer, and it'll be enough to actually get a spark or to light up a neon lamp. And a neon lamp, we don't really use neon lamps much anymore. If you looked at old power supplies from how many of you are audiophiles, really into amplifiers or speakers? Okay. What amps do you like? Okay. 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 All right. So that's probably mainly digital for most of it. Okay. So you look at really old, I'm into valve and tube amps, really old amps, okay? And if you look at really old amps, there'd be this little flickering light when you turn on the power. That's actually a neon lamp. It needs really high voltages, hundreds of volts, to turn on. And just to show you, you can take one of those neon lamps, put it next to a crystal, whack the crystal, and it'll momentarily light up. Now, I said it's hammer time. Does anybody get the cultural reference, or am I too old? So, yeah. Okay, so every now and then I used to give a lecture for HKN, which is our EECS Honor Society. I used to give a lecture on sort of crazy stuff you can do. And I started doing that about 10 years ago. And each year, when I mention this, I find less students get it. Which makes sense. I'm getting older, but you guys aren't, right? So, but anyway, there was a rapper. This is a long time ago. This was 1990, I guess, was when he was big. So he called MC Hammer. He lives in Oakland, actually. He lives here in the Bay Area, okay? So anyway, and he used to sing, he used to do a lot of stuff related to that. I was in college at that time, okay? So that's my excuse. All right. Now, basically what you do is you take a good-sized crystal, you place some aluminum foil on it with Vaseline to just hold it down, and you connect the wires to a neon lamp, and when you hit it, when you whack it with a hammer, you can actually light up a neon lamp. It's amazing. It really works. You're not limited to just using piezoelectricity. You can make your own batteries. So, for example, you can make batteries by combining different metals together and immersing them in an electrolyte. One very well-known example is the potato battery. Okay? What you do is you take a potato and you stick 2 pins with dissimilar metals into it, and the potato is moist and has some electrolytes in it, and it turns out you'll be able to measure a voltage and get decent current out of it. So you can make a potato battery, and this 0.5 volts, by the way, is enough. If you put 3 potatoes in series, it's actually enough to run an LED. Okay, and you can actually do it. So cool things for first dates, right? These are awesome. So, all right, okay. So there's a lot of interesting stuff you can do, but that's stuff. Now let's talk about interesting people, okay? And we're going to start by talking about radio, because a lot of really neat things happened in radio. All right, so before we had cell phones, we had telegraphs, okay? Telegraphs used Morse code, or what became called Morse code, to send messages over long distances. I'm assuming most of you don't know Morse. Anyone knows Morse? Probably not. Okay. No, the code. Okay, yeah. So Morse is basically a series of long and short tones. Okay, so we call it, actually you probably do know some Morse, because you've heard of did da 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 did, which is SOS. Okay, there's some things that everybody sort of learned that, well, maybe when I was a kid we used to learn these sorts of things. All right, anyway, right after we'd ride our dinosaurs into school, we would learn these things, right? So anyway, the Morse was used to send over long distances. It actually used to use wires, and then they actually found a way to do it over long distances. Now, boy, that's Pony Express, not Poly Express, okay? But actually, it turned out that there was a connection from the east coast of the US to the west coast of the US by the mid-1800s, and that is what finally killed off the Pony Express. Why is that important? Because once that happened, the next step was actually wire transfers, and once that happened, the era of the gunslinger was gone. So wireless, and actually telegraphy more specifically, is what got rid of cowboys and the like, and as a result, we no longer have good movies about cowboys, right? So all those cowboy movies ended in the 1800s. That's why, because telegraphy got rid of the need for having the Pony Express. You didn't have the Pony Express, you didn't need people to go riding across the country with messages or carrying money. If there weren't people riding across the country carrying money, we didn't need outlaws to steal from them, okay? So telegraph cables were pretty important, but it was missing something. It required a wire, and it didn't allow voice. Now, but they went pretty far. They had a transatlantic cable where they actually ran a cable across the Atlantic Ocean by, again, 1866. It wasn't very reliable. It only worked a few days before it failed. But it turned out it was very important. The reasons for the failure led to some of the stuff that you learn about if you take EE 117. Okay, that's when a lot of that physics developed. Okay, it was pretty clear that we needed to get away from wires. Depending on cables is unreliable. So we wanted to get to something that could be wireless. So the first well-known transmission was called the spark gap transmission, and that was by Marconi that's 1885, sorry, not 1985. Okay? The spark gap transmission is actually something you've probably experienced. So if you are listening to the radio, and depending on the quality of your radio, if someone turns on a fluorescent bulb near you, you hear a crackling sound on the radio, especially on AM stations, not so much on FM. But on AM stations, it happens. The reason for that is there's a spark, and a spark turns out to be a very broad spectrum sound. It covers a large, range of frequencies, and it overlaps in your AM radio transmission, and you hear that little crackling sound. So Marconi showed that you could use a spark gap, so you'd essentially create a spark, and then a radio in the distance would pick it up as a crackle. That's useless on its own, but if you combine that with Morse, maybe you could start sending information, right? So that's what Marconi set about to do. The first AM radio was by Fessenden, and that was in the early 1900s, and a shortwave radio followed that. The first FM radio was 1931. First digital radio was in 2000. Okay, first commercial digital radio was in 2000. And today this has become, of course, very important. Okay, so the first real radio broadcast, and I'm going to tell you some interesting stories about this, was a spark gap. Okay, literally what he had was he had two electrodes that were placed really close together, and by applying a voltage, he would get a spark to go through the electrodes. The spark would generate signals in a coil, which would send a radio wave out from an antenna. He would have a receiver, which would be the inverse of this, somewhere else, connected to a speaker, and you would hear a little crackling sound. It was digital transmission, because he had no way to modulate it. He was just sending little crackling sounds, and each crackling sound represented a bit. Okay? So, now, here's the interesting thing. It turns out that those same sparks, your teeth is if you have fillings, it's a wonderful receiver. So your teeth will actually start vibrating if you do a spark gap experiment. So, okay. Now, why was that important? It turns out, just as is the case today, everything was driven by sports. And Marconi contracted with the New York Herald and the Evening Telegram to provide up-to-the-minute coverage of the America's Cup yacht race. So you know what the America's Cup is. It's still an important yacht race today. It's a yacht race that occurs between European and American teams. And the problem was that was taking place in Europe, and Americans wanted to know how their yachts were doing. So Marconi said, well, I will use my spark gap, and I'll send you information. We'll agree on some way to encode it, and I'll send you these sparks, and then you'll know who's winning. And it actually worked reasonably well. So he was fairly successful doing that. It worked pretty well. He apparently did pretty well. But that was in the 1899 America's Cup. But you know how it works. One guy does it, it works well. So as soon as that happens, a bunch of other people jump on as well. Now you're going to see a problem. So for the 1901 America's Cup, we had Marconi, and we had AT&T. And we had a guy who's really interesting called Lee DeForest. And they all said, we're going to do spark gap. The problem is, spark gap is non-selective. There's no dial to set the frequency. So if everybody's broadcasting at the same time, you don't hear anybody. So 1901, we had the first network wars, and nobody could hear anything. Okay. So we needed a tuned wireless system. So how did that come about? Really, the main progress came when we had semiconductors. So let's talk about semiconductors briefly. I'm going to talk about them now a little bit, then we'll forget them for several weeks, and then we'll come back and talk about them again. Anybody know why we use the term semiconductor? What does a semiconductor mean to you? Yeah. That's a reasonable way to say it. He said a semiconductor is, a normal conductor conducts all the time. A semiconductor, you can sort of set how much it conducts. Maybe it can conduct sometimes and not others. That's correct. In fact, a semiconductor has two properties. One is, as he said, Well, actually, one is it has its intrinsic conductivity is somewhere between that of an insulator and a conductor. So a conductor would be, for example, copper. An insulator would be, for example, glass. A semiconductor will sit somewhere between those two in terms of conductivity. But what's really important, and this is the point he was making, you can build devices out of semiconductors that modulate that conductivity. Namely, they switch it on or they switch it off, or they amplify or they reduce, and that is the basis for semiconductors. And we will spend some time on those in this class. The first real semiconductors that we used were called coherers. Basically, a coherer was a tube, an evacuated tube, that was filled with loosely packed metallic powder. And it turned out it kind of acted like a diode, which means it conducted current in one direction but not really in the other. Nobody can really explain why it works. Okay, it's sort of black magic. But it kind of does. It normally has a high resistance, but it goes to a low resistance when exposed to an electromagnetic field. So that means you could detect a spark, because when the spark would come through, an electromagnetic field would be generated. It would drop to a low resistance, and you could detect that. So you could use it for detection. Problem was it was sort of irreversible by default. So once it went to a low resistance field, you couldn't get back to a high resistance field until you whacked it with a hammer. Okay? And you whacked it with a hammer, and then it would go back to the high resistance state. So early spark gap systems that use coherers, you'd sit there and you'd get these bits of data coming in, and then every now and then the system would degrade down so it wasn't working anymore. You whack it with a hammer, and then you do it again. Yeah, question. What do you mean? Oh, very good. So, I'm too slow. That was good. Okay, so anyway, this is people made circuits using these coherers, and what you would do is you'd have an antenna on a coil, and you'd connect the coil across a coherer, and then when the incident spark gap signal came in, the resistance of the coherer would change, and then you could detect it. And then, as I said, you'd have to sort of just whack it to get it back into shape. Okay, but all of that is meaningless. Let's talk about real transmission. Let's talk about actual radio. So you've heard of AM and FM radio. What does AM mean? Amplitude modulated, and FM is frequency modulated. What does that mean? Here's what we do. In an AM system, we have a carrier wave that is oscillating at a particular frequency. For example, the traffic signal that most of us in the Bay Area listen to is 740 AM. Okay, that's at 740 kilohertz. And what we do is we modulate a signal onto it. And what that means by modulating a signal onto it is, let's say I want to modulate a sine wave onto my carrier wave. What that means is I change the amplitude of the sine wave, of the carrier wave, such that the shape of the amplitude box is a sine wave. And so if I can make a system that can then just figure out what the shape of the outside box is, I've then got a radio. And that's amplitude modulation. Okay? And here's an early AM station that was on the East Coast, I believe. I don't remember exactly where. And then to demodulate, you do the opposite. You take your incoming signal. Actually, let's walk through this on the board so that you'll see how this works. So if I have a signal like this, okay? If I draw the outer box, the envelope of this, it's something like that. And I want to extract it. One thing I can do, if I wanted to extract it, is I could just take a really slow circuit, right? A really slow circuit is not going to sense all these sharp movements, and it's going to track the average. I essentially take a system that does a moving average. If I do a moving average off this, it sort of follows the envelope, right? The only problem is, because this is going positive and negative, the moving average is 0, because it's going positive and negative, so it cancels out. So all I need to do is cut off half the signal. If I can get rid of this, and then I take the moving average, I will, just using a really, really slow circuit, I will get a signal that looks like that, and I can put this to my loudspeaker, and I can hear the radio. That's what a simple AM radio is. You can make these radios. These are called batteryless radios. All you do is you take an antenna, and you connect it to a diode. The diode cuts off half the signal. It only allows the positive side through, loses the negative, and then you put it through a capacitor, and the capacitor is essentially a moving average system. It sort of smooths everything out. You don't see the high frequency part. You only get the low frequency part. And you can put loudspeakers across this, and you can listen. Yes? How does it cut out the high frequency? Ah, that's a good question. Okay, so it turns out that a capacitor, the amount of current that a capacitor will allow to flow through it depends on the frequency. Higher frequencies are able to go through capacitors more easily than low frequencies. So the high frequencies just go through the capacitor and don't get to the loudspeaker. The low frequencies get to the loudspeaker. Okay, that's conceptually the idea. And we'll talk more about that when we talk about impedance. Okay? So that's the basic idea. You can build these. You can actually buy these at Radio Shack. They're called crystal radios or batteryless radios. And they work reasonably well. Okay? It's basically a coil, a tuning capacitor to set the frequency, a diode, and a high impedance headphone. No battery. And you can listen to AM radio. It works. It's not great. The quality is usually not good. If you are near a strong AM station, you can actually hear it reasonably well. And here in the Bay Area, 740 AM is a strong station. So you can actually build it and listen without a battery. Okay. Early transmitters were all spark gap systems, which means this was a transmitter which had a motor with a rotating piece that would sort of go underneath, and every time it came underneath, it would create a spark. And so this is how they send signals. Early detectors, as I said, used coherers and the like. Okay? The big change that happened in now almost 200 years ago was the development of vacuum tubes, which were the precursors to transistors. And they actually looked like this. This is a real vacuum tube, and what it made a diode. And then you could use this to detect that envelope, that thing over there, and get true AM radio. Many of you may, well, some of you may know that in the early days, you've probably watched movies where they show this, where you turn on the radio and then you let it sit for a while before the signal actually comes in. That was because the vacuum tubes had to get warm. Because the way the vacuum tubes work is they have electrons that get excited thermally, so the vacuum tubes actually have to warm up. And that was kind of how these things worked. Okay. The biggest change was when we got semiconductors. The idea of semiconductors was described a long time ago. Braun described semiconductors in 1874, primarily sulfide species, galena, iron pyrites, which is fool's gold. You're probably familiar with that. There's several others. Silicon and silicon-related compounds came much later in the early 1900s, and that, of course, was the starting point of research on semiconductors. The earliest semiconductor diodes were called cat's whisker diodes. To be honest, for many, many years, when I first learned about cat's whisker diodes, I always thought there was really a cat's whisker inside. Turns out that's not true, okay? But the reason it's called a cat's whisker diode is this is essentially what it looks like. There's a piece of semiconductor here, and then there's a very, very thin wire which just barely touches down on the semiconductor. And the reason they do that is it turns out the semiconductor quality was really poor. So if you had a big contact, you'd usually get a defect. But if you had a really, really, really tiny contact, you might get lucky and find a spot that was clean. Okay? So in fact, in the early cat's whisker diodes, you would just sort of sit there and just keep wiggling it around and keep trying till you found a point where you got a good signal. In World War I, they used to make diodes for the soldiers in the trenches used to make radios to listen to the news or to listen to wartime reporting using cat's whisker diodes, where they would take razor blades. The razor blades were stainless steel, but they would oxidize, and that would form a semiconductor. And then they would take thin wires that they would shave and just sit there and sort of keep touching, make a coil, keep touching it, move it around until they found a signal. So much easier to use a digital radio today. But this is literally how these systems used to work. Okay, now we're getting to the cool stuff to mess with your landlord. All right, you can make your own semiconducting diodes in your apartments. Here's what you do. You take a penny, but it has to be a penny that's after 1983, okay? The reason for that is actually kind of interesting. Anybody know how much a penny is worth? More than a penny. If you melt a penny down, you actually have the metal component of, actually that's not true today, but till recently it was true that the components of a penny, the metal inside the penny was worth more than a penny. Okay? You've learned something, right? I'm not going to take you all the way there because that would be illegal. Okay? But you now have a way to supplement your income. So, okay. No, but seriously, this was, that is illegal to melt US currency. Okay, apparently you can go to jail. So I've heard. Okay? So, but apparently, anyway, the idea is if you take pennies, if you take the penny, older pennies didn't work because they were a homogeneous alloy of copper and zinc. And the zinc poisoned the copper so it wouldn't form a semiconductor. Copper is more expensive than zinc. So new pennies, and by new pennies I mean pennies after 1983, to save on copper cost, so that they didn't want the penny to be worth more than a penny, what they did was most of the penny was made of zinc. And just it was plated with a thin layer of copper on the outside. Okay? And copper turns out to be a good material to make a semiconductor. If you take copper and you clean it, okay, by just rubbing it very nicely with something soft to just clean it off and get rid of the oils, and then you oxidize it. So what you do is you clean it and you stick it in an oven and heat the oven up to about 500 Fahrenheit, okay, maybe a little bit longer. So many ovens don't get up to 500 that well, so you can crank it up or put it on the clean cycle for an extended period. And this is why you don't want to do it in your oven, do it in someone else's oven, okay? And then what it'll do is it'll actually oxidize the penny, and it turns out to be uniformly coated. It's gone to this sort of rich chocolatey brown color, okay? And that is copper oxide, and it turns out copper oxide is a semiconductor. So you can make your own diode. Take the penny, lock it down onto some sort of substrate, and then take some sort of safety pin or a pencil lead, the graphite, to touch down just barely and just kind of move it around. And you can measure the current voltage characteristics, and at some point you'll find it's a diode. Okay? Works very easily. It's not difficult to do. I've done this. Okay? It works quite well. As you can see, I'm extremely cool and I have lots of free time. You know, I spend stuff on this. So, okay. You can then make that into a radio. So this is a crystal radio that you can make. You can buy these kits in Radio Shack, but there's no reason to do that. You could make it yourself. It's just an inductor and a capacitor. The capacitor is used to tune the resonant frequency for the radio station. Then you've got your penny, your copper oxide diode, and then you have a high impedance headset. Regular headphones don't work. Anybody know why? Like if you took your iPhone headphones or your iPod headphones, those don't work. Anybody know why? No, it's not the frequency. Their resistance is too low. They consume too much power. And since this system doesn't have any batteries, you need a very, very high impedance headphone, something that really doesn't draw much current. And they exist. They're called crystal headphones. They're not very popular anymore. But the advantage is they don't draw much power. The problem is the sound quality is not very good. But they do exist. And you can use it. It's called a batteryless radio. Works fine. Okay. You can take another step. And this is just another version on this that someone else came up with afterwards. And that is called a regenerative radio, where what you do is you say, well, I'm using the RF to make a batteryless radio, but given that there's lots of radio frequency power available, I can even use that to essentially generate a power supply for local use. And that's what this circuit does. It essentially has a batteryless radio plus an amplifier, and the amplifier power comes from the radio itself. And that gives slightly better sound quality. And these are kits that you can buy as well. Okay, this is that foxhole radio I was mentioning, where in World War I, they would take a rusty razor blade, iron oxide is a semiconductor, and then they would essentially make that into a diode and then try to use a headset to get radio transmission. You don't see these stops. You can't do this anymore because this is the old style razor blade. You know, most of you, well, I obviously don't shave, okay, but most of you probably use the, track 2 or track 3. I don't know if you remember the old style razor blades. Does anybody know what I'm talking about? Yeah, there's little square things. Those things actually are typically coated with a thin oxide to make them last, because those blades are not intended to be thrown away on a regular basis. Use them for a long time, then you replace them, and use them for a long time, and then you replace them. And so those, because they were coated with this oxide to make them harder, that was a semiconductor. Okay. So the first modern vacuum tube type semiconducting device was called the Audion. This is an interesting story, but it was patented by a guy named Lee DeForest. It's almost certain that he stole the idea from another guy named Fleming. And the reason is he could never explain how it worked. But Fleming could explain it perfectly. Now, there's a lesson out of this. When you write answers on your tests, when I give you questions on the tests, I will always ask you why, if I ask a question. And you will find I will give you 0 credit if you get the right answer but cannot explain it. But I will give you partial credit if you give the wrong answer but have a reasonably consistent explanation for why your wrong answer was the answer that you gave. Okay? All right. So people built radios using these sorts of systems. They worked really well. There's sort of interesting stories. Lee DeForest was, so Armstrong came up with this really nice radio. Lee DeForest hated Armstrong, and he publicly insulted Armstrong. Lee DeForest couldn't explain how his invention worked. Armstrong could. It's pretty clear that Lee DeForest stole the idea. Armstrong, however, still lost the lawsuit in court, and he committed suicide. So a lot of crazy people, a lot of money to be made, and unfortunately in this case the bad guy won. Okay. Now, I mentioned something earlier, and I showed you a picture, and I didn't really explain it. So let me introduce a new device for you today. And this is a device we are going to talk about reasonably soon, and you'll use a variant of this in the labs later. I mentioned earlier that you want to be able to tune your receiver. When I showed you that batteryless radio, I said you have a capacitor that you use to tune the receiver. Modern AM radios do this digitally, okay, so it's not so important. But in old AM radios, there was a knob that you would turn to tune to the station that you wanted. Okay? What does tuning mean? It's changing the frequency, right? How do you change the frequency? You change the frequency at which the antenna absorbs. The antenna is made up of a coil and a capacitor. The coil is fixed. You don't change its value. But you change the capacitance of the capacitor. Okay. Can anybody define, if I asked you, most of you have taken high school physics, and I would assume you probably are aware of what a capacitor is. If I were to ask you to make the simplest capacitor you could for me, how would you do it? Someone. Yeah, in the back. Yeah, that's perfectly good. I would take some insulator, like a ceramic, and I would slap an aluminum foil on the top and the bottom. That's a capacitor. A capacitor is 2 conductive plates, for example, separated by an insulator. Okay, what sets the value of the capacitance? I've taken that sandwich of 2 aluminum foils separated by a ceramic, and I want to know the capacitance. What sets the value? Yeah. Correct. The capacitance value is set by the surface area, namely how big those aluminum foils were, and the spacing, and one more thing. Yep. The dielectric constant, namely essentially the quality of the dielectric. Okay, namely how capacitive that ceramic layer was. Okay, now, I don't really have an option. When I make a capacitor, I'm kind of stuck with whatever dielectric I use. It's not like I can have it change its dielectric constant. I also have a relatively fixed gap, okay? I have the two plates. They're separated by a fixed distance. One way I can make a tuning circuit to tune my radio is by having two plates, and I rotate them with respect to each other. And when the two plates line up, I get maximum capacitance. And when the two plates are off axis with respect to each other, I've got a low capacitance. And by setting the angle, I continuously vary the capacitance. That is the knob in your old radios. Not in new radios. New radios, it's all digital. But in old radios, the capacitor was essentially this. It was a plate and a rotating plate, and the overlap of the rotating plate and the fixed plate set the capacitance, and that set the tuned frequency, and that set whether you were listening to 740 AM or 860 AM, for example. Okay. And it got pretty sophisticated. They would actually make multiple tuned circuits, all running off multiple capacitors that all rotated with respect to each other. They're beautiful to look at. If you ever get a chance, go to the Berkeley Flea Market. Is actually excellent for buying really, really old radios. And buy one just to open it up and look at the cool mechanics. I mean, these are just neat. You know, the sophistication of the mechanical constructs is remarkable. All these little foils that move with respect to each other, they're beautiful. Okay. We'll end on the radio note by talking about really what was the last real radios that were used before digital took over. Okay, these are gone. Today it's all digital. Okay, but for almost half a century, this is how all good radios were made. The problem with radios was you would always hear nearby channels. So if you were listening to 740 AM and there was a broadcast at 720 or 710, you'd hear a little bit of that. And so what they wanted to do was they wanted to have a way to really, really tune very tightly. And they would do that by essentially having a series of filters set one after the other that were really, really precise in the way they worked. Now, it turns out it's really difficult to design a filter that is tunable and precise. So if I design a filter and it's really, really good at 740, but then I change its tuning to be at 710 or 860, it's never as precise. So that made it difficult to have a good quality radio that you could also vary the frequency of. So what they did was they came up with a super heterodyne radio, where what we would do is no matter what frequency we had coming in, which we could tune it to 740 or 860 or what have you, we would then shift it to a known frequency. And that frequency was actually 455 kilohertz. And then all the rest of our circuits would be really high quality circuits designed to operate at 455. And so we would get really high quality sound with really good separation of channels because we would get rid of all the other spurious stuff because we would shift everything to the right frequency. And this was called a super heterodyne receiver. Very, very widespread. All major receivers were made this way for 50 odd years. Today, nobody makes receivers this way because what you do today is you get your signal in, you digitize it, and you do everything in a microprocessor. Okay? Okay. What enabled microprocessors and the starting point for the modern age of electronics was transistors. And there was a Nobel Prize for transistors. It went to 3 people, Shockley, Bardeen, and Brittain. They were all at Bell Labs. Interesting story. So as I said, I'm a Stanford graduate, but that doesn't mean I can't make fun of Stanford. I like Cal better. Okay? Shockley, and most people don't know this, after Shockley got the Nobel Prize, he got recruited to, we should turn off the webcast. I don't want people to hear this. But anyway, no, Shockley got recruited to Stanford as a professor. And he went to Stanford as a professor, and he was there for, I believe, 20 odd years. And in that time, I think he only graduated 1 PhD student. This is the rumor I heard, okay? And he did publish a few papers, but none of them were on electrical engineering. He started expounding on eugenics. Anybody know what eugenics is? Yeah, it's the theory of racial superiority and racial differentiation, how certain races are better at certain things than other races. And Shockley was not, it's not like he was saying oh, whites are the best, or something like that. He was just saying races are different. But he basically devoted his whole career after the Nobel Prize to that. So, maybe that's what Stanford does to you. So, all right. So early transistor-based systems evolved out of the work of Bell Labs. So Bell Labs was the research arm of AT&T. Bell Labs didn't get it. They didn't realize how useful this was. And they kind of treated it as a research topic. And instead, people used vacuum tubes for the early radios. So the first transistor radios appeared in the 1950s. And they didn't work that well, but they were small. And when you turned them on, they worked instantaneously. You didn't have to wait for them to heat up. So they were absolutely revolutionary. They could run on a battery because they didn't have high voltages. The vacuum tubes needed high voltages. So these were absolutely groundbreaking. What is a transistor? Well, this is not the transistor that was used in the original device. But this is a transistor that is used in all modern devices, including your phones, etc. And this is basically what we call a MOSFET, or a field effect transistor. It's a switch. We have two electrodes called the source and drain. They're separated from each other by something called a channel. The channel normally blocks current flow. So under normal situations, there's no current flow between the source and drain. But when we put a voltage on the gate, the channel allows current to flow between the source and the drain. So we've made a switch. It's a switch that turns on depending on the voltage on the gate. More importantly, for the early transistor radios, the amount of current depended on the amount of voltage applied. So you could make an amplifier. And we will talk about that in this class. We will talk about simple amplifier designs. Okay? So you can think of a transistor in two ways. From a digital perspective, it's a switch. From an analog perspective, it's an amplifier. Okay. Transistors on their own were used as discretes. You can still buy them today. You can go to Radio Shack and buy individual transistors. In some of the things you're going to be working on, you will use discrete components in the labs. But really, most of what we do today uses integrated circuits. This is the first integrated circuit. By the way, he got a Nobel Prize recently. The integrated circuit received a Nobel Prize. And the integrated circuit was first invented, well, by two people, arguably, Jack Kilby of Texas Instruments and Robert Noyce of what was Fairchild Semiconductor. You may know who Robert Noyce is. He was one of the founders of Intel. Okay? And an integrated circuit was basically a device that combined multiple components on it. It had a transistor, and it had a few other things. In this case, it had a resistor, a transistor, and a couple of wires. Okay? But basically, what he showed is you don't need to have individual transistors and wire them together by hand. Rather, you can build them all on a single chip. And that's a relatively modern integrated circuit, and it'll have millions or billions of transistors all on one chip. Okay? And that's why do we do that? Because it's cheap, and we get lots of functionality, and it's high performance. Why are ICs important? Because they eliminate wiring. We get to pack everything into tiny circuits. They run better, they run more reliably, they run faster, and they are cheaper to build. And that's why we build them this way. Okay? Anybody know? I don't know if I have the data on here. Let me see. No, okay, I don't have it on there. I'll get back to you on the exact numbers. I just checked recently. I believe right now, for every person on the planet, we make about 1 million transistors. Something like that. Each one of you, for each person on the planet, doesn't matter how old you are, we make 1 million odd transistors. Yeah. Yeah, because remember, what's the total population? No, I think maybe it's 1 billion transistors. That's probably what it is. Yeah, it's probably what it is. Okay, so let's stop there. We'll start on the real material in the next class. Remember, Monday morning lab is canceled. It's rolled into Wednesday. Okay? No discussions next week.